So I'm hoping that I can convince you all that there's more to be said about kind of designing robots and soft robots in particular than just design, but also kind of how the manufacturing fits into that. And between soft robots and additive manufacturing with molten glass, which is the other research that my group does, I really like sitting at the intersection of design and manufacturing. So I actually named my group the Fabrication Integrated Design Lab. See if
While we click on the screen.
yeah, I can just do that. Oh, right, because the controls come up from okay. So I have kind of a group of people working with me. Like I said, we're at the intersection of machine design and manufacturing, and I used to draw my Venn diagram with soft robotics in that blue area. I like to say that I work more so with materials than on materials, but I do like working with challenging materials, applying them to applications that is a bit non-traditional. So whether that's soft robots or now also within glass fabrication. With the glass, we're using that for structural masonry, essentially taking recycled glass and turning that into load-bearing walls, then that could be part of a larger building or structure. Just click here. Okay, so why is it interesting for me to work in soft robotics? Well, I have a background in mechanical engineering from MIT as an undergrad, but I also worked in industry as a manufacturing engineer, first for medical devices, and then in micro and nano fabrication and a little bit of water treatment. And so kind of I'm looking at areas where I've always kind of played between that and then glass blowing, which I've done for almost 20 years now and have been a technical instructor at MIT in glass blowing for almost 15 years. And looking at spaces where there's an intersection of design and manufacturing, that becomes interesting in soft robots because as a nascent field, we're building new machines that I would argue should not be built the way that you build a rigid machine. You could bolt or braze or glue soft robots together, but anyone who's tried, I'm sure, has experienced the pleasure that is lots of delamination. So we should think about kind of new ways to kind of design with these new materials, new functions like structures and manufacturing. For example, even if I tell you, if you were, let's say you're me, you were taught to design rigid machines by saying everything is rigid and you should aim for small deformations. This doesn't make sense for soft robots because I would say some of the most successful ones are ones that actually leverage large deformations. Great, so large deformations, good, but then you look at the software that a lot of us are using. Even if I say that I want to design new machines that look different and leverage large deformations, I'm using SolidWorks for the most part, or Fusion 360, to then design soft robots. So I'm using software that was designed to design and fabricate rigid systems to then build novel soft systems. I don't know about you, but I see some issues with that. Not to say that we're designing necessarily new software, but we're thinking about kind of how can we get specifically new functionality out of soft machines, and how does that change kind of how we both design them and fabricate them? Coming from industry, I'm usually focused then on functionality. And so then you ask the question of kind of what function should then drive my innovation. For me, in my PhD, that was deep sea biological sampling. And so I made this gripper. This picture was taken at about 600 or 700 meters underwater. And we're just picking up a sea cucumber here. Not very interesting for most marine biologists, but a great demonstration that we can sustain kind of the deep sea environment, both the corrosive salinity and the deep sea pressures, while still then being gentle. If this animal feels threatened, it'll avert its stomach as a stress response. You see that it has not done that. We have given this holothurian a nice hug and then put it down again. And what that did was to be able to convince the marine biologists and the ROV pilots, deep sea ROV pilots that I work with, that we can be trusted to then pick up something more precious like endangered coral. The reason you want to be nice to endangered coral is it's actually an animal. When you stress it out, it changes its DNA response. If you then change your DNA response, then you invalidate the data that you're collecting on said DNA to help preserve those animals. So when I'm on a deep sea mission, it looks something like this. I'll be on a ship like the Nautilus with the Ocean Exploration Trust out of University of Rhode Island. And then I don't go in the water. You could not pay me enough to go in the water. Instead, we send an ROV like Hercules here into the water. So that's the yellow-topped ROV. Out of Hercules, we have one bubble cam, usually is mostly what we're looking out of. And then we're using a large rigid manipulator made of titanium. Those are craft arms to then pick something up. And it looks something like this. You're trying to pick up something often squishy that has a complex shape. and is often quite mobile until you then squish it. And then it is no longer mobile. So you have things that are compliant, complex shapes, those can crumble. Really, it's not just that it's tricky to move around these shapes because they themselves are also compliant. You end up crunching them and dropping large pieces of these, which aside from just looking bad on live broadcast, is really not great for the scientific mission of these. And it's not to say that these ROV pilots are doing a bad job. It's mostly that it's a hard task. So I pioneered this with Kevin Galloway and Rob Wood's group in about 2015 or 16 was the date for the prototype on the left, and that went 300 meters underwater in the Red Sea. And then one of my later prototypes is here in the American Museum of Natural History, and that went down to 3,500, 4,000 meters underwater. And the nice thing about these grippers is that they're compliant enough that they can start to actually adapt to the things that they're picking up and not crush those. So in addition to being gentle and not stressing the animals out, you're actually more likely to be successful because you can conform to the object that you're picking up. Also, because I'm using mostly silicones and plastics for this, they're actually quite inert to the corrosive salinity that is actually really problematic for a lot of rigid manipulators. They're so inert actually that I can use salt water as my working fluid. And so when I'm in the deep sea, I'm actually just using a pump to pump in salt water and then use that to hydraulically actuate these grippers. And then if I spring a leak, I'm not leaking hydraulic fluid into the coral colonies that we're trying to study. It's actually quite safe. And so that starts to look something like this. Unfortunately, I have for you the videos from 2015, 2016. So this is not one of those nice craft arms. This is a Hydrolec arm, which is actually quite shaky and not wonderful. This is actually the craft arm. The audio for this one is actually really wonderful, where the ROV pilot's saying like, oh, you really couldn't do that with a rigid gripper. We would have just crunched through this. Okay, so soft robots are already pretty good at this, but my job as an engineer is to look at how we could make them better. And I take a fabrication integrated design approach to look at how we can tune soft contact. I'll first show you just very briefly tuning contact at the surface. So imagine if you could turn the friction at your fingertips on and off, what that might look like. And then how we can actually mechanically program these through design and fabrication so that the underlying structure is actually passively doing what we want and limiting forces and adapting to the things that we're picking up. From there, looking at distributed arrays of contact, what does that mean? It means I have two types of grippers here for you, whether it's a more deterministic contact where I have a traditional kind of sausage finger and a spherical grasp, or I start applying stochastic contacts that are distributed randomly and are individually gentle, but sum up to a more robust grasp. And then from that, I'll wrap up with a little bit of what we're doing currently, tiny bit of sensing, but more so kind of moving forward into the control area. And I don't mean controls, I mean basically how to power these things. Okay, so altogether, there's 4 different kind of major areas where we're thinking about how to take a fabrication integrated design approach to really mechanically programming these, at least an open loop, to then do things that are helpful in the deep sea. And presuming that kind of, if we can operate in a deep sea environment and making these things more reliable, then we can translate that to terrestrial applications as well. Okay, this one is the shortest of those 4 categories. This is really just the tunable friction. The idea here is that these are really high friction materials, the silicone rubbers, and you often get stuck on something. And so when we got stuck on a slime star trying to pick it up, I thought, well, wouldn't it be nice if we could actually turn that friction on and off? So in this demo, actually, the actuation pressure of the fingers doesn't change at all. It's just the finger pads get turned on and off. So essentially, I'm turning friction on and off as I then manipulate this light bulb into place. The way I do that is with a high friction deformable membrane that's then constrained by a perforated low friction layer. So when I inflate that internal high friction membrane, it grows polyps through the fingertips that then come into contact with the object that I'm picking up. So I can pick between a high friction and a low friction surface. Okay, like I said, that was really going to be the shortest one. But then moving on into structural adaptation, just a little reminder of kind of what this then looks like. The videos I showed you earlier were very clear. This is much more typical for what it looks like. There's a lot of marine snow floating around. I'm picking up something that's kind of a complex shape. I have limited vision because of that marine snow and the shadows and the outcropping overhead. And not only is my shape a little bit hard to pick up, it doesn't want to be picked up. And so my job is to then make sure that the pilot can basically just reach blindly under that outcropping and press a button, and the fingers will adapt to that crab and pick it up gently, because I don't actually want to pick it up if I can't pick it up gently, especially on, again, live broadcasts. Really bad look for these universities. Okay, so the question is, how do I program that into the underlying structure? I asked the marine biologist, what are these creatures going to look like? And they're like, I don't know. We sometimes don't know. We're not sure what we're going to pick up. And I pressed them further, I pressed them further. They finally said, you know what? If you can pick up a pretzel rod and not break it, we'll let you near the coral. So I tried to pick up a pretzel rod, and this clearly was not going to work, right? And I did some like very basic modeling, just kind of like super basic physics simulation like you would have in a phone game. And basically from that got to the conclusion, like, I'm not going to get here with the current manufacturing methods I'm using and these materials. But if we just add some more materials for selective strain limiting, if you think of this as a beam, as you inflate that beam, it becomes fatter. That means it has a higher bending moment, which means it's less likely to bend. But if you put a girdle on that beam, then you can actually restrict some of that deformation. So with the same operating pressure, you get more curling. And then you can also kind of add in that open cell, very important that it's open cell memory foam, to add kind of another limit of strain. So the nice thing about the memory foam is you have a nonlinear stress strain response. And so between 10 and 50% of compression, I can basically say between my underlying structure and the foam, then I am limiting this to 10 kPa of contact pressure. I told you I was only I sort of implied that I was only going to talk about 2 different actuators. I lied, there's this one more. The reason being that with the other blue actuators, the contact pressure is so low that it just looks like noise on this sensor array. But basically we confirm that we have something that is gentle enough that that we can both conform but not crush the objects that we're picking up, and then also confirm that we have enough payload to actually pick them up. But because I'm the manufacturing engineer I want to point out that one of the most important things about this is that they operate reliably. It costs about $60,000 a day at the time to operate one of these boats. I'm not obviously the only scientist on there. I'm just one support person. There's a whole team of scientists that are making use of this boat for the day. And basically what we do is we deploy the ROV, it goes into the water, it takes about 3 to 4 hours to get down to depth. And so if my actuators were to pop a leak at depth, they're not going to bring the ROV back up just to repair my squishy robot fingers. They're going to go on without me, which means these have to work really reliably. And the trick for me was actually digging into the manufacturing. So by making these monolithically, so casting all as one piece, we use a soft core that can define a complex internal geometry and then basically get manhandled out like a complex gummy bear. So you've defined the internal geometry and the external geometry in one molding step without any seams. That doubles the operating pressure. If you go deeper in the rabbit hole of manufacturing and look at the specific technology that we're using to print the molds and where basically the support material shows up, without then changing the geometry, you can double the operating pressure, just moving around where support material is essentially, and looking at kind of where defects show up in the manufacturing process. With that, you can then essentially totally, in total, quadruple the operating pressure and increase the cycles to failure by more than an order of magnitude without any changes to geometry. Topology optimization and kind of geometric optimization is very important, but aside from that, what I'm trying to convince you of is that manufacturing also matters. And if you think about the fact that I was able to do that with manual molding process, now we're transitioning that to injection molding, and I've made a relatively inexpensive lab scale injection molding setup to do this so that we're taking out some of the potential errors from the manual process. And so this costs us probably around like between $500 and $600 if you include the like structural framing that we use to attach it in, which is very expensive but very convenient to use. It's 80/20. Okay, then looking further into that, I won't go far into this, but one of my students, Charlotte Felinas, is actually going to present some art based on this ongoing work, and we've submitted for publication, looking at kind of then different failure modes if you were to bond. So if you can't make something monolithically, because there are plenty of scenarios where you shouldn't make something monolithically, how do things fail, and how do you kind of selectively, strategically start selecting materials that make sense for that particular application. I would say we're fairly guilty of, and it makes sense within soft robotics, of saying, well, I just kind of picked it because it was what was accessible, what was affordable, what I had on hand in lab. These are all valid reasons to use a material, but I think we can go further into why we select certain materials. And it shouldn't just be durometer, and this had the highest elongation to failure. It's a rabbit hole that I will leave for Charlotte's papers that are not yet out, but I would say that there's more that we should leverage from rigid machine design, but we should also be mindful of the fact that we should select our materials based on slightly different criteria. With that, though, there are other ways to improve bonding between interfaces. So Kat last year presented at RoboSoft using flocking, basically fuzzy surfaces to increase our adhesion between rigid and soft parts, so we can start making more complex soft rigid hybrids. Essentially, flocking is an industrial scale process where you just apply fibers to things, like jewelry cases, for example, or like tchotchkes that you can get at the toy store. But because it exists on a a large scale process, you can take either 3D printed or injection molded parts, flock them, and then embed them with direct over molding with our injection molding setup. And so it gives us some freedom to get a little bit more wild with some of the geometries. And this was inspired by a lot of the kind of high surface area transitions you see in sea star ossicles and soft coral sclerites. I won't get into the data, I'm just flashing it. The conclusion is essentially within pull tests and peel tests, it's not going to vastly outperform things like some of the RTV glues that you can use already, but the design space that it opens up allows you to get a much more complex geometry. And then with that, you can then increase the adhesion between the soft and the rigid layers by basically reducing the stress concentration between them. Okay, once you've then gone through and said, there are things that I can do within manufacturing to improve the robustness of these, you might then ask, well, how do I go about designing them? And there are other people who are certainly doing kind of much more extensive computational work on here. But what we're doing kind of with Annie Doris's work is then saying, how do I start thinking about these with manufacturing kind of in the loop and human in the loop, and just giving some basic tools for people who, like me, were trained to design rigid systems to then wrap their head around how to design soft systems. So this is not meant to be groundbreaking from a computational standpoint, but be a tool that a designer can actually use to start understanding how different parameters affect the design. Both doing kind of a parameter sweep and a grid search is a very naive way of exploring the space, then also having the option of an evolutionary search. Hopefully everybody can still hear me over the ambulance. I said, raise a hand or something on Zoom if you can't. But the idea is that you have a very transparent process here, where then you can use that to help kind of build up an intuition of how these different parameters then affect the performance of your design, but then also tie into manufacturing limitations and start to get a more nuanced approach of like the different performance metrics that we care about. The example that I often give is, I don't want to just optimize a soft gripper to curl at the lowest pressure possible. If you do that, you have made a weak gripper. What I care about in the deep sea applications, for example, is I would like to close and have a certain grasping force at a specific point of closure. I care about also the bandwidth and the energy and the max stress in different areas. And actually what I care about most changes from different contexts. So giving us a tool to help navigate that. But that is also assuming that I know what I want. And sometimes I don't know what I need, like in the case of being in the Channel Islands Conservatory, where the marine biologist had never been there before and had no idea what it was we were going to pick up. So how do you design a gripper when you don't know what you're going to pick up? Also, how do you design a gripper for something that is topologically complex like this? You saw, I spoiled it for you in playing the earlier video too long. You know that this glassy sea sponge is not going to break. But I will tell you that I did not know what that was going to do before the gripper closed around that. So A, we don't always know what we're going to see when we're down there. B, even if it's in front of us on a camera, we don't know what those mechanical properties are going to look like. Also, it's just a difficult shape to pick up. So instead of then making grippers that I can precisely place a contact around, I decided to move into a more stochastic direction. So we love soft robots, right? Because they're compliant. And soft robots are difficult to deal with because they're compliant and they're hard to plan for. So what if we take a stochastic approach where we just throw a lot of contacts at something and each individual contact is very weak and gentle, but then the whole is greater than the sum of its parts? Because then you have the friction with the filaments in the object that you're picking up. You also have the friction between the filaments. Okay, so this is kind of in the distributed contact realm, the bottom left here. And the idea is that you're letting the object actually define the shape of the gripper itself. And so by adding to material compliance, also structural compliance, then you have more adaptability. These are actually just either pneumatic or hydraulic actuators. We've tested them down to 900 meters underwater, but mostly use them for terrestrial testing. It's essentially an asymmetric tube. So when you inflate it, the thinner side inflates more and it buckles and it curls. And so the filament gripper that I'm showing you right now is basically 12 filaments. The way we make this is what made it kind of was important into kind of making this a very easily iterated process. I essentially use something that looks like candle dipping. So if you think about candle dipping is you take a string and you dip it in wax, or the way they make balloons and doctor's gloves, you just dip a open form into kind of liquid rubber, and they're using the surface tension to get a constant film thickness. That means I can get very high aspect ratios of very large parts with a very consistent thickness. For anybody familiar with manufacturing, having a really big differential in your largest dimension and your smallest dimension and maintaining precision is actually really hard, but I get that for free through passive physical properties. But if I have a constant film thickness, I haven't really made an interesting actuator. So I add some more kind of passive forces. We'll have this, yeah. And I put them in the wrong order, sorry. So with this, with the passive forces, basically, I probably am in the wrong order of slides, but essentially I can use electric fields, surface tension, fiber inclusions, or then gravity to then mechanically program these and bias the thickness. So I take the same really inexpensive molds that are like dollars at best, or at worst, I should say, and then use that to then add some programming element. And with that, I can then program the direction of motion, I can program my operational pressure, the curvature, and the grip force. So I have kind of a map of manufacturing recipes that get me to this. And here's the slide that I thought I was going to show you last time. I won't belabor this, but again, kind of there's different ways that I can use passive forces or kind of an active fiber inclusion to then mechanically program these so that they actually bend in the direction that I want them to bend. And what that looks like, just briefly, is in the top, I have a 256 kind of macrocilia array that are programmed by gravity. And in the bottom, I have a like 150-ish macrocilia array that then has an arbitrary vector field programmed in. And so these are interesting to then play with marine biologists who look at different ciliary beating systems so that we can then recreate some of those behaviors. But if you make those longer, that's how I make these grippers. So these are all gravity programmed. And then again, with this 12 filament gripper, the object that I'm picking up actually defines the shape of the grasp and the amount of entanglement. The amount of entanglement, how much those filaments twist around an object is kind of hard to measure because they're squishy. I can't just take a pair of calipers and like prod through this. So what I do is I then take CT scans of them. And so we have a three-dimensional reconstruction of the object inside of the gripper, and then can trace that to get a vectorized format of the orientation of all of those filaments. From there, we can do a little bit of math and say, we can actually quantify how entangled it is. And so taking some cues from topological knot theory and Buck and Simon, I actually use an open form of an average crossing number, not a total crossing number, but an average crossing number to quantify how robust this grasp is. Now, an average crossing number is essentially if you take a mesoscopic sphere of a portion of this gripper, so like just one view, and then you smash it so that it's flat, and you count how many times it's crossed over each of the filaments, that's a crossing number. An average crossing number, and what this double integral describes, is if you take an average of all the different possible orientations of that, and then average them and say that's your average crossing number, and then an indication of how entangled these are. Now, you can plot that as kind of like a density function in space. You can also look at the total average crossing number, which for each of these grasps sounds uninteresting. They're all about 14. But If you then look at the object on the right, as your object starts looking more filamentous, you can then include that in the average crossing number, and that jumps to about like 21, 22. So that's the kind of very rigorous math way of saying, this is really good at picking up things that kind of look like filaments, which you might be able to intuit from how this looks, but it gives you a way of actually evaluating that in real time. That has inspired kind of some of the ongoing work we have with sensorization of these and kind of where to move forward and thinking about kind of the different contact points. One of the interesting things is I don't really need all of the filaments to contact something. And what I have on the right here is a simulation, and the left is a, unfortunately, hand-counted physical picture. But not all of those filaments actually contact the object. They are still, though, participating because they then contact each other and increase the stiffness of that overall grasp. And you can think about that as a distribution of contacts, like we have in red, of filament to object, and also spatial distribution of contacts between filaments. That's something that we can start looking at, kind of how the friction then contributes to this, and also maybe how it might be impactful if we modify that friction.
Can I ask a question?
Yeah, absolutely, please.
How do you get these filament to filament contacts and also the filament to object contacts identified? Do you live in the CT scanner, or was this manual annotation?
The Mira software. It's Daniel Baum at Berlin. Actually, is an expert and kind of works in with Amira software. And so we use some of that stock software and then some modifications to help clean it up a little bit more quickly. I think you can do it with the stock software. It's more painful because there's really thin walls that make it really hard.
And then this way you can actually identify these points of no air gaps, but full contact. And that's what you.
Yeah, exactly. Yeah. Okay, then what I'm showing here is just to kind of show you again, it is indeed a stochastic process. So I have 6 different grasps that will be overlaid. And so each different grasp is actually different, but it indeed ends up being kind of the same result. Then we have done like thousands of trials with these, but it's difficult to do then thousands of trials with many, many different iterations of this gripper. So fortunately, I was able to work with someone from Professor Mahadev's group at Harvard. And this is actually Matteo Gazzola's software, but then modified by someone else, Nikki Charles, who is in Mahadev's group. The limitation of this software here is it actually doesn't actually simulate static friction. We're only doing dynamic friction here. And so it'll vastly underpredict the performance of these grippers, but then makes it a little bit more tractable for the simulation. There are different groups who've been able to then add static friction that they assure me is then going to be tractable, but we haven't tried it yet. Okay, so we can then compare all of these, but moving through, then if I plot essentially those different parameters that are showing that we're varying, we can vary both the object spatial density and the filament spatial density, and then map out kind of what we think the performance is going to be. Those then individual points here are where we then validated that with an experiment. And I would say the experiments are very uninteresting in that out of 20 trials, we almost never drop the object. And so then to get an idea of whether we're actually appropriately mapping the performance space with the simulation, what we do is we then start messing with the gripper and saying, okay, we basically apply a positioning error. So the robot arm thinks the object's going to be in one spot and we purposely move it, increasing the error to then test sensitivity in that way, and then get a similar trend that we see from the simulation. The other thing I'm showing here is also then what happens if you increase the weight of the object itself. Pretty obvious, as the object gets heavier, then our overall performance goes down a little bit. Okay, so we've gone through structural, tunable contact, and distributed contact. But now thinking about how to power some of these, and this is not necessarily something that we would do in the deep sea, but one of my students who's co-advised with Ellen Roche is going to present on this at RoboSoft next month. And shout out if anybody is looking for an excellent postdoc, Sam is about to graduate. Sam has been working on monopropellant power for these and thinking about kind of how can we harvest then some of the energy that we get from applying hydrogen peroxide to just a silver catalyst as a way to very compactly store power, but then also deliver that in a way where we can have local kind of power distribution. So in a traditional format, you would actually take a central fuel tank and then pump that out to a reactor that then powers an actuator. And the clever thing Sam thought to do was, I'm not sure if he was inspired by the deep sea pumps, but the deep sea pumps we use actually they look like a normal pump with then a flexible membrane on the side so that it automatically adapts to gauge pressure. So in the deep sea, I don't need to know that I'm X number of meters down plus a little bit of differential. Instead, it actually just that flexible membrane automatically adapts to what the local pressure is, and then you get a differential on top of that. So then what Sam did was to then add a flexible membrane to an engine that he implants inside of an actuator. So you can have a low pressure central fuel tank that's then pumping at low pressure a little bit of fuel into this engine with a built-in catalyst. And so that then pressurizes this green membrane here. I don't know if, can people on Zoom see my mouse? Okay, great. So this green membrane then gets inflated a little bit with some of the fuel. And because you have a check valve behind that, it doesn't flow back. Then we can release that into the fuel reactor and it starts building up pressure. As you build up pressure, so the actuator pressurizes, then it's normalized because that flexible membrane is between the actuator and the engine that is inside of the actuator, then it can still continue to build pressure on top of that. So you use it as like a pressure amplifier for a local delivery of a monopropellant. And so the benefit is if you compare what a traditional actuator would be able to do versus then Sam's engine, you can get to a much higher pressure. I won't go into a lot of the details, but I would encourage anybody who's going to be at RoboSoft to check out Sam's poster, and I'm going to find out if he's giving a talk. But just to show you a little bit what this looks like in actual physical hardware for the first prototype, we've got kind of a 3D printed prototype here with a little valve. And then implanted into a small soft gripper, you have a finger for size here. Hopefully this works. This will give you an idea of the actuation speed. So basically it's a very simple demo, but when the button is pressed, the light goes on. So you have an idea of when he's triggered the actuation and then how long it takes for that reaction. Oh, I'm so sorry. It's 0.15 speed. I put Sam's picture over the timestamp. But you can see that's a fairly fast reaction time. What is important to note, though, if you look at this gripper, it's going to show up again with some of the other work that we're doing in designing grippers specifically to be able to operate with a very low actuation volume. And so in addition to thinking about kind of what power we have, also kind of how do we route that essentially. I'll take a momentary deviation from that and thinking about once we have lots of different channels, how do we then start dealing with all of the tubing that's associated with these systems? You can see that I have very selectively cropped the bottom picture, for example, so you don't see the 16.25-inch tubes, 6mm tubes coming out of the top of it. And then the mass of like rat's nests attached to that with barbs and such. And so some of the work that I did with Nicholas Bartlett at Harvard was then to couple some soft like microfluidic or mesofluidic fabrication with some of these dip-coated actuators. So we made a demultiplexer that then could be directly integrated into some of these soft actuators, making a 2 degrees of freedom version as far as kind of the direction of actuation by taking 3 input channels. So in this particular example, we have 4 logical inputs. Those are the ones on the left, and then 2 static inputs, the red and the yellow on the right. And so from that, we're able to get 16 outputs by just logical combinations between those different valves. Okay, but then a different way of routing power, and then it's a different actuator on the left here, but related to the one from Sam's monopropellant engine. We can start thinking about, are there ways that we can improve upon the soft core molding method that I showed you earlier to give us more compact complexity, to give us more freedom to have complex channels and then import some logic into those channels themselves? So what Qifeng has done is basically made our version of a low volume core. We can't say it's no volume, but it's very low volume, where he actually uses just a cricket, like so a simple kind of cutting machine to then cut little pieces of plastic and then bond them together to make these soft cores that get basically molded into an open face mold, and then can give him several different actuators that are tuned for different pressures, and then a logic gate or kind of a valve in between them that then adds a little bit of a delay. So then in this demonstration, let me go back. What he's doing is essentially just inputting a square wave of pressure, pressure on, pressure off, but by a combination of designing the actuators and inputting embedded logic that are all monolithically molded together, he can get a more complex output. What this looks like is essentially little pieces of plastic that are bonded together, just a little cookie cutter that he then molds over kind of in one shot. And this can be done with like open face casting, or we've also done it with injection molding. You'll see a demonstration of what the demolding then looks like. So remember I mentioned kind of like pulling a gummy bear out. Now your gummy bear has gone on a significant diet and it's just a flat little fan that comes out of here. And we have measured the force of extraction. I'm forgetting now, I think it's on the order of like 20 newtons, 10 or 20 newtons. So not significant for the complexity of what he's pulling out of there. And so because the core can then deform very significantly, you can get that complex structure without a lot of force to remove. Also, by having a smaller core, then for SAM's applications, we have much less dead volume. So those operate much more efficiently for the amount of volume or for the amount of monopropellant that SAM has to use. The additional nice piece here is by having a much smaller interior chamber, then your stresses in bending the overall structure are much lower. So you have a high number of cycles to failure for these. But I think what becomes interesting is then we can get much more compact complexity in here. So then we can use this to make a 4-chamber finger, for example, to get multiple degrees of freedom inside of a gripper. This is not something that I could have done with those soft cores that I showed you earlier. And so with that, you can start taking kind of 90-degree bends and putting more complex functionality into the grippers as far as kind of what sort of shapes that they can articulate. With that, I mentioned we can put valves in. We have both a check valve, so it's mostly just restricting flow or slowing flow either way, but then also pinch valves. So you can have something where instead of just a passive effect, you can actually actively pinch off or slow down some of the pressure going in different directions. I won't go into the details, but basically similar to some of the earlier stuff, we've then just with the fabrication recipes then characterize how much flow we can block or change the throughput through these valves. And then so if you start thinking about kind of both SAM's engine and then the actuators, you can start tuning each individual actuator to then operate at a certain actuation pressure, but then start modulating the valves either passively or actively. So then we look at how we convert a relatively simple square wave into kind of more complex motion. The one thing that we're really missing here is then a phase shift, but one thing we're able to do to then compensate for that a little bit is by then tuning the actuation pressure of the different intermediate actuators and playing with then kind of how we differentiate that with the pressures of the pinch valves in between. So then if you have, you can both play with your square wave input here, and you can also play with the relative pressures of the different valves. And it's a little bit hard to see, but it's essentially like a similar actuation time. Then you get a different amount of travel by playing with both the frequency of actuation and then the pressure of the individual valves. And then so skipping into, then just a tiny bit of sensing, and I won't go far into this because it's not published yet, but I just wanted to preview then some of what Nina's been working on is then how do we have or create scalable ways to then integrate sensing into these large arrays and ways that are then compatible with the molding themselves. And so she's figuring out ways to then, with a relatively small number of sensors that are easy to then kind of more mass produce and embed in the fabrication system that we have for making those arrays themselves, then start to accomplish some proprioception and exteroception. And then previous work that we'll hopefully kind of circle back to is then taking kind of much more precise molding. So in a previous life in industry, what I worked on was then taking silicon masters and then doing high throughput replicas and producing these at a fidelity that basically accomplishes features at the size scale of like a 10th or a 50th of the diameter of your hair. And these are basically photonic sensors for Raman spectrometers that would be more so for chemical detection that we could then build into the surfaces of soft actuators. And then that's related to kind of work that we've done previously with embedding waveguides into the actuators. And so I know that you have faculty here working on this as well, but then being able to use these waveguides for then both proprioception and exteroception. So when the actuator bends, it kind of reduces the amount of light that you have going through the waveguide itself. And you can use that if you compare it to kind of what your predicted loss of light is, then some amount of proprioception, but also exteroception if you've bumped into something. And so in the deep sea context, that glassy sea sponge, for example, we might get more feedback as far as kind of how soft or squishy something really is before we commit to grasping it. And with that, that's all I have to show you on the soft robotics side. I thought I would just briefly mention some of the glass that we're working on. Again, the connection here is working with materials that are kind of then applied to non-traditional applications where you might see them. So we normally build rigid robots. We're now moving to soft materials, now kind of moving into the glass realm. We mostly don't think of glass as a very strong material. But there's definitely lots of research that's shown that we can use float glass and cast glass for structural materials. Sorry, these were timed. This is Daniel Massimino's work, and we're working with Evenline. So Evenline is mostly Michael Stern, who's one of the founding members of the MIT glass printer at MIT that I helped consult on. And so we've gotten started a collaboration where we're working on structural masonry that's 3D printed. But we're also then 3D printing with recycled glass. So we take container glass, so think about like a wine bottle or a gin bottle, if you will, which is really what the top one is, because it has a nice blue color. You can now guess which our favorite brand is, or taking float glass and then turning that into structural masonry. And the nice thing with the float glass is then if you print with float glass, then you have a compatible material with then float sheet. And so we can print directly on sheet to then either have facades or basically stiffening against wind shear loads, or using it just as a hybrid manufacturing technique. I'm happy to talk more about that, but I wanted to limit how much I talk about glass at the moment and leave some time for questions. Thank you all for listening.
Questions for people?
Talking about sensing, proprioceptive sensing of these fingers, for example.
Yeah.
Is that with optical methods?
I can't totally tell you because it's not. I mean, how about this? You've seen that I've done some things with waveguides. So we do use some light sensing in there. Those aren't particularly waveguides. But yeah, I think some of the easiest ways to implement sensing into soft actuators that you could assume that we're probably using. Yep, I've shown you that we use some optical sensors. Strain sensors are a pretty easy way to go too. And then using some information about kind of the models that we already have for how much something should bend or how much we expect something to bend under given pressure. And then once you start having multiple signals, kind of how do those interplay? Yeah.
I was curious, when you were using your filament actuator, did you ever encounter sometimes the issue of the filaments staying entangled together?
Yeah, I get this question a lot.
The payload like moves around, I suppose, then it could not open anymore.
Yeah, out of thousands of actuation trials, only once have I ever had them stay somewhat entangled, maybe twice. And the solution is you actuate it again and release again, and then it disentangles itself. If you think about it, you don't have a lot of shear going on. If you actuate them all at the same time or in the same direction, they're coiling and then pulling back in the same direction. To get a knot, you kind of have to have them then interweave. And so it's difficult from the way that we're actuating these for them to tangle with each other. And then there's always like the possibility of, you know, if you do get entangled though, they're not so much knotted, which is why I use the average crossing number as opposed to in topological knot theory, there are no knots in here. If you actually dig into the math, I have not made a knot. To make a knot, I would have to actually kind of twist them around more and then kind of tie them together. But from this standpoint, it's really just the friction between filaments that's holding them together. Yeah. Yeah.
So you showed some examples where I guess you're embedding some, and it doesn't have to be the example he mentioned, it could be a different one, but that you can talk about. But you know, how are you actually, I guess, what you're using dip molding mostly for sort of the integration of these, or are there other manufacturing methods that you're thinking about for sort of integration of both the rigid, soft, and electromechanical?
Yeah. So we are doing a bunch with injection molding and over molding. So that's a great way to get kind of more complexity and integrate rigid and soft components. And it's actually related to, I teach a manufacturing course at MIT where my students all have to make yo-yos and they have to do some over molding. So they over mold like metal hardware into the plastic yo-yos. And so it's a little bit inspired by that. It's a scalable method that already exists. I mean, if you look at toothbrushes, for example, or even this clicker has some over molding on it. Yeah, so over molding from an injection molding standpoint, but then also dip molding. I look at kind of ways where I can attach basically I can attach components to a mold that I have embedded in rubber and then kind of pull it away from the mold. And then the tricky part ends up being positioning. But for the fiber inclusions, for example, that's an overmolding example with the dip molding, I guess. And so I bond the fibers, or I just tack the fibers to the pins that I'm using as my open face mold is what I would call it, because it's a 1-part mold. So I tack the fibers on and then just dip the whole thing essentially.
Yeah, I can see if you're like attaching it directly to the mold surface, it's pretty easy, but if you have to locate it inside of the object, then it gets really rough.
Yes, yeah, and there are fun ways to do that. Sometimes I do that with kind of suspending things across textiles, and then the whole textile stays is left behind. And so in that, so the predecessor to this filament paper was the dip molding paper, and for that, basically, I use a lot of cheesecloth as a way to kind of embed things. I've helped other people use then metal meshes and different things, for example, for embedding magnets so that they don't rip themselves through soft actuators. Yeah, but clever things with textiles works. And then actually, if you pre-mold certain things out of the same rubber or a soft enough material, and then you just suspend it as either a sacrificial structure that stays behind in your soft actuator or something that then can be pulled out after.
And it just has to get hot enough that they can kind of properly bond.
It doesn't have to get hot at all. Yeah, so it's they're actually thermosets, not thermoplastics. Yeah, so you're actually cross-linking. So that's why it's a 2-part polymer. And so you have to, once you mix the 2 parts, you have a certain pot life. Actually fun, well, nerdy fact, I guess, is that I think pot life and mixed viscosity are 2 of the most underappreciated variables of rubbers that can have a huge impact in your eventual kind of, in both the manufacturing and your eventual performance. And we don't think about it traditionally. Yeah.
So I have a question for you from Alexia online. Alexia Legal, she's asking, thank you so much for the fascinating talk. I'm curious, what inspired you to focus on pneumatic and fluidic actuation?
Yeah, so it's a great question. I think that was an application-driven one. If we're actuating in the deep sea, deep sea pumps are readily available. I mean, they're expensive because they have to be rated for deep sea, but I can get a hydraulic pump. And so that constrained a lot of our design space of thinking kind of what makes sense to integrate with the existing system such that, you know, we can limit both the cost and complexity of installing these on an ROV. And so the nice thing about hydraulics is A, the pumps exist, and B, when I'm 4,000 meters underwater, I don't have to worry about shorts. I don't have to worry about kind of compression or pinching on cables, for example. And it's something that's relatively easy to trigger. So basically there's a cable, there's a tether that attaches all the way down to the ROV and that sends both power and communication. And so then a signal just says pump turn on, the pump turns on and flows through. And we can do the really simple and dumb thing of just having a limit pressure. So before we could afford having an accumulator, which is kind of like a pneumatic capacitor, before we could afford that and we just had a pump, we essentially said, just turn the pump on, don't worry about the pressure. We got a swage lock fitting that we could set to 25 PSI, which is about 170-ish KPA, I think. So it's simple and will work repeatably under high pressure and won't make the ROV pilots hate us.
Okay. I had a question.
Yeah.
when you design your sort of pleated designs or these like fast net designs.
Yeah, yeah,
And you go to a steadily increasingly thinner, or like not increasingly, a thinner and thinner wall, because you want to have these sheets that can nicely fold together.
Yeah.
So pulling them out. And I saw you had also
yeah.
multiple of these, right?
yeah,
And sort of like cardboard almost, they will, or not cardboard, like they will fold together.
Yeah.
So you pull them out. But at the same time, you make the inner cavities smaller and smaller and smaller.
yeah,
While probably the exterior still stays roughly the design that you wanted it to have. So have you studied the relationships of the inner wall thickness to the outer bulk material?
Yeah,
and
yeah.
What have you found?
That's a great question. So it actually, so this was preceded by Annie's work started, the simulation started before the thin, like the low volume cores.
Mhm.
And the low volume cores then shot ahead of the simulation work. But it was basically informed by the modeling that Annie had done.
Mhm.
And we were getting to the point where the modeling was telling us that we wanted to get, and hopefully this comes out soon in a publication, everybody cross your fingers for me. What it came out is that, a person, okay, I don't need to.
We will take up, don't worry. Keep
Okay,
going.
okay, sounds good. Basically, you get higher performance with or at least lower stress in the sidewalls if you can reduce the core dimensions or the core thickness. Because basically what you're doing is you're essentially, you're moving the walls with a thicker core, you're moving the walls further and further from the neutral axis. And so they have to undergo larger strain to get to the same amount of like bending deformation. Now that does also, there are trade-offs there with the stiffness and the strength of your actuators I pointed out before. But what we want to move more towards is more of a reconfiguration of materials. So even if we can undergo large or support large strain, the wear and tear is lower if we can limit that to, let's say, under 30%. And we haven't done kind of the full study of kind of that balance. More so we've done kind of what Annie started, and it shows us kind of how we want to go a little bit thinner. But what I showed was actually much more naive, just kind of first stab at dimensions. So that one's not optimized at all. And I think something that we can revisit with Annie's tool and haven't done yet. So I will hopefully get back to you in the near future, like what that looks like.
Because I mean, traditionally you would, let's say, have maybe 3 times that thickness per chamber.
Yeah,
But let's
yeah.
say you now have 3 of them.
You're saying 3 times the thickness of, sorry.
The interior cavity.
Yeah.
But
Yep.
now you've done down to
Yeah.
maybe, what is it, like a millimeter in thickness?
Yeah, just barely sub-millimeter.
Yeah, and so now let's say your original 3 millimeters, you split it up into 3, yeah?
Mhm, Yep.
Have you looked into that relationship and how that affects your performance?
Yeah. No, we haven't yet. Yeah.
So
That's
like,
a good.
because you would then in the end still have the same amount of volume, but maybe get a very different information. I know you want. To
Yeah,
minimize the
absolutely. Yeah,
volume
because you
for
have,
the most
yeah.
it helps, but like.
Yeah, because then, I mean, you could then capitalize on that too for like selective antagonistic actuation and potentially do a kind of sequential actuation for more interesting deformations. But we haven't looked at it yet, so yeah, it's a good one. We should use that, but haven't done it yet.
Good. Next one, Charlie.
Hi, hope you can hear me. Lower my hand. Cool. Thank you so much for the talk. I particularly like the flocking paper you had. I was curious if, or how, if and how, flocking would scale with the sort of desired final product. Like, for example, the entangling sort of tentacles you have up. What if I wanted to make them 3 millimeters, 2 millimeters in diameter? Would the kind of, depending on the flocking material method you use, I just don't know how that scales with what you're trying to combine.
Yeah, I was a bit cagey about what we're doing with flocking.
Sure.
Plans for mostly for integrating rigid and soft components. So potentially you could use some of the flocking to help anchor the filaments, but the filaments actually have the ones that I'm showing on the screen right now, for example, have no fibers or rigid materials in them. From kind of those connectors downward, it's just rubber. It's just a tube of rubber that's capped in the bottom. So I'll split maybe your question into 2 different ones. So the scaling of the filaments, which don't involve flocking, it gets challenging as you move thinner. You need a higher actuation pressure to get the hoop strain essentially is what you want, or the stretching of the rubber itself to then create the like eccentric elongation on one side of the filament. You just need a higher pressure to exert the same amount of force because you have a smaller area over which it's applied. Then as you scale up, your limiter becomes, you don't need as high of a pressure to get deformation, but because your material is further, if you think about this as like beam bending, because your material is further from the neutral axis, it needs to deform more to get the same amount of curvature. So then you're basically sustaining higher strains in the filaments themselves. That's kind of like the trade-off. And so what I have here, I think this is like they're 4 millimeters approximately as like a average diameter of like the major and minor diameter, because they're actually kind of elliptical in cross section. But it's kind of a sweet spot. If I go much smaller, I also then hit fabrication limitations in the surface tension of the rubber. What then happens is the rubber kind of balls up on one side of the pins that I use, which potentially we can modify the surface tension to get even smaller. But I haven't gotten to a point where I'm willing to deal with that yet. And then flocking, I don't know if you want to modify it at all, but I would say for the flocking, we use like a $20 tube. It's a cardboard tube inside a cardboard tube, and it looks a little bit like a shaker you would use to dispense like shredded cheese. And you use that to kind of puff. Somebody's sound is on, just so you know. You might want to mute yourself. Okay, thanks, Rob. But yeah, it looks kind of like a cheese dispenser, what you might use for inexpensive Parmesan cheese, at least in US markets. I don't know if you can get the same thing here. And they sell it for actually like model train use, but then it exists in obviously industrial scale because they do use that for commercial products and inexpensive commercial products. So you could put that on injection molded materials or printed materials. I'm not sure if there's like maybe a more helpful thing to clarify about how that would scale. If you're thinking about size scale instead of production scale, I'm happy to change my answer or modify my answer.
I think I'm asking more about size scale.
There's components in car construction that actually have been flocked because you can use it actually both for optical purposes to reduce glare and also for acoustic purposes to then kind of dampen sound. So what they do for a really large scale is actually, I mean, you use, I think something akin to like the spray guns you would use to paint a car, and you put these in big booths. By the way, this is something that you should do outside or in a chemical hood. Yeah, I mean, you can try it at home, but try it at home in outside.
Somebody else's house.
They do, they do sell these kits for people who are making like model train setups and things. But yeah, you can do this on very large components too. You just need bigger equipment than I have. I think the limiter for us ends up being, it's a little bit annoying to then, what we do is we brush the adhesive on and then spray the flocking or poof the flocking, if you will. And then it's just kind of an awkward timing situation. And so if you wanted to do this at a larger lab scale, I would get kind of what they use for like model scale spray painting. And if you want to do it industrial scale, then it's still spray painting, but they have equipment for this. And I think it looks like what you would use again to do to paint a car, to detail a car.
Are these type of materials things you could use powder coating for, like electrostatically charged?
Oh yeah, I'm sorry, thank you. That's
Yeah.
oh, and that actually we do have results that does actually help. Because so it's mostly what we use was like rayon fibers was like easily accessible. We thought the cotton performs very well, but you can't get that commercially. We actually chopped up a bunch of cotton fibers, which was terrible. And I did help because I didn't want my grad student just doing that by themselves. So I sat there and chopped cotton fibers as well. But you can buy rayon fibers, and using these guys, you can actually then you can buy a little electrostatic guns to help the fibers actually stand on end. It's actually very important that they stand on end, and they do this in the commercial processes where they do actually have an electric field that's helping with that. Because obviously, or maybe not obviously, if those fibers then kind of drift into the rubber, they're not sticking out and helping you with that mechanical engagement. That's actually quite important. Thank you for asking or for pointing that out. Sometimes I forget the details. I'm like, oh yeah, that's right. That's really important. Remember that thing.
Someone was so innovative and asked in our Q&A function on Zoom, which I've actually not used myself. a question.
Yeah.
Anonymously, so I don't know who. The question is, what's the number one challenge in simulating the soft grip of finger? Do standard finite element simulation software have the right capabilities?
I'm probably not the best person to ask because I think my talents are much more in the fabrication. And my students are actually much better at the finite element analysis than I am. But I would say one of the things that I've seen as a pain point, and I think this applies to CAD as well, different CAD software, is I think the like freeform ability to modify or come up with geometries that are not kind of very heavily influenced by existing archetypal kind of construction methods within that software, if that makes sense. And so I think for me, it's an innovation standpoint of how do we build something that doesn't look like what we've been conditioned to build all along and what our kind of training tells us. The other thing is, I guess, you know, if you're going with large deformations, it's very easy to kind of inappropriately mesh, deformations and large differentials in dimensions. It's really easy to blow up a model if you're kind of spanning like very different stiffnesses and at an interface and different dimensions. So somewhere between that, I've peeved off, let's say, lots of models. And then also I think the kind of ability to kind of vary things where it's not just kind of, we mostly use Python scripts to then automate kind of exploration of a design space, but that means you have to be able to parameterize it in a way that then restricts some of that kind of creative development.
Great. So thank you very much. Okay, let's give a hand of applause.